I'm Larry, N6NC from San Diego, and this is a presentation on a 7-month study I did to try to figure out why we have very good and then sometimes anomalously superb 40-meter CW propagation between San Diego and Japan. A question that's bothered me for probably 12 years. Just to go back, the anomalous event that I looked at occurred on July 24th, 2010. You'll all remember that Alex, the E3NEA, invented the CW skimmer software around 2008. And that's, if any of you aren't familiar, what it does is take the output from a receiver in a wide bandwidth and decode and save the CW station's call sign, the date, time, frequency, signal to noise ratio, and CW speed. And then that information, if your skimmer is connected on the internet to the reverse beacon network, all those spots, huge files, are archived by year and month. So it's available for parsing as Excel files at later dates. I had one of the earliest skimmers in San Diego, and I had set it up. I've always been interested in 7 megahertz propagation for 2 reasons. One, we had always been able to work the Pacific Island de-expeditions later in the evening with virtually no pileups from the West Coast on 40 meters. And also because we had, during contests, sometimes we were able to sit there on 40 meters and run JA stations for hours on 40 meters at night. So and don't forget, this is 6,000-mile Great Circle path between San Diego and let's say Tokyo. Anyway, first of all, I had built some antennas of my own. I had a 2-element parasitic vertical array aimed directly at Japan. My QTH is about 700 yards from the Pacific Ocean on a slight hill. And what I did was set up a timer so that the CW skimmer would copy any Asian and particularly JA call signs that it heard on CW over the night. I started that in 2008. The results in 2008 and 2009 were maybe a handful of JA contacts copied by the skimmer overnight. And that was just kind of interesting to me. But then suddenly on July 24th, 2010, I got up in the morning to check the night traffic recorded by the skimmer. And to my surprise, there were 141 JA call signs listed. A couple of them were dupes too, but it was an enormous number of call signs. I couldn't figure out why. I immediately emailed a very well-known Japanese contester, TAC JE1CKA, and TAC said that what astonished him was that 85% of the JA signals were 5-watt CW stations participating in the JA Summer Domestic CW contest. So that was kind of interesting. The average, I went to the RBN to check, and the average of those 141 spots was a signal to noise ratio of 10.9 dBi, which was pretty strong, especially considering the weak 5-watt stations involved. Next slide, please. Oh, you got it. Sorry, you're ahead of me. I also, in the last few years, happened to get a master's at Scripps Institution of Oceanography. And I've sailed the Pacific Ocean back and forth all around the coasts on both sides. And I was always interested in the propagation and meteorological effects across the Pacific Ocean. First, I started looking around for US Navy radio operators from World War II, who I suspected would have at least an anecdotal understanding of why there were these enhanced propagation events over the Pacific. Also, I noticed on that particular July day from the RBN that my 141 spots constituted 14% of all the JA spots recorded around the world from Japan that day, which was a very high percentage. I tried to check WSPR, PSK, and GPS total electron content data, but there really wasn't much back then in 2010. And the data was either inapposite or didn't exist for July 2010. Then I went to VOACAP propagation data. There are two, you can see on the slide there are two very good ham interfaces for the VOACAP program. Basically, VOACAP was a study undertaken by the Voice of America, I think in 1949, and with the database built on since then, to show likely propagation circuit success from various transmitter spots around the world to various other locations. Next slide, please. One more. There we go. This is what's called the VOACAP propagation wheel. This is for the dates at 9 Zulu during the time of recording of the spots at my skimmer. And if you look at the right around the 6 o'clock area, that dark orange band of 1, 2, 3, 5 or 6 units, that's the 40-meter likelihood of propagation success between Japan, specifically between Tokyo and San Diego for that date in July. And you can see from the color code below, that's above 90% circuit reliability for that July date, which really kind of surprised me. And that's 5 hours a day of 91% circuit reliability from that VOACAP. So I took that information and I contacted Carl, K9LA, who's one of the ARL propagation gurus. Carl's written articles for years in all the ham magazines. And he's an RF engineer with a lot of industry experience and who's done a lot of ham propagation experiments on his own. He has the PROPLAB software, which uses the VOACAP data for a specific date, time, and location, and it'll run proposed models of propagation circuits between the points that you ask it to. Carl ran it for me. He got two models out of his attempt, and this is the 3-hop 2 surface reflection model that for 7 megahertz on the date and time in question. There was a 5-hop model, but that to me that had too many potentially moving parts to come into line to make it work. And as it turns out, a study that I found later said that really on between 3 and 18 megahertz, the most you can get is 2 surface reflections off the ocean. And you have to be above 18 megahertz, 18 to 30, to have more surface reflection points. So I think we properly discarded the 5-hop model. Now, Carl likes to use when he's evaluating a particular circuit path, he likes to have an ionosonde right in the middle of the path. Unfortunately, across the Pacific, there are not ionosondes on the Great Circle path, so we were kind of out of luck on that. But I researched a little bit and found that there are ionosondes pretty close to each end of the path. One at the northern end of Hokkaido Island, Japan, the northernmost island, and the other at Point Arguello, Vandenberg Air Force Base, which is near Santa Barbara, California, a little north of Los Angeles. And by the way, if any of you are interested, I just caught the end of Gwen Griffith's presentation. If you want to know more about ionosondes and ionograms, Eric Nichols, KL7AJ, has an excellent piece in the January 2022 QST at pages 65 to 68, which explains a lot. So here's the ionogram for Point Arguello ionosonde on 724. Basically, my understanding is if you look at the red prints, it shows you the maximum usable frequency, MUF, which you can see there is in the dots is about 3.3 megahertz, too low for 7 megahertz propagation. But interestingly, look at the scalar on the bottom of the ionogram where I've got the red oval, and it shows what low angle rays, how far out they can go, and what MUF, maximum usable frequency, will be produced at very low angles. And the reason for this is the ionosphere, don't forget, this is dark Pacific at night. The ionospheric stimulation from solar radiation is gone as it cools during the evening. And but if you go the long distances, for instance, you can see there's two that are of interest. The 1500 meter scale is 7.4 megahertz, and the 3000 kilometer scale has an MUF up to 12.3. So there are possible low angle 40 meter paths across the Pacific with those ionosonde readings. And by the way, the Hokkaido ionosonde for the same date and time showed precisely the same long path, low angle long path, 7 megahertz propagation. And anyway, the point I wanted to make was the reason they have these long hops at low angles is, if you think about it, don't forget the way RF works. This is oversimplified, but basically it refracts in the ionosphere. That's kind of like when you put a ruler in a glass of water and you see the offset image because of the differential medium. And RF reflects basically off the ground or particularly ocean surfaces. We'll get into that in more detail. And going at a long distance, the ray eventually goes through enough of an ionized area to start bending it by refraction back down toward the ocean surface. Okay, got the next slide. So anyway, then now I went ahead and put the numbers in, the kilometer numbers from the PROPLAB model, and with the red ovals at the ocean surface reflection points for the 3-hop propagation model for that date and time. I was concerned about the potential loss of signal at the two RF graze points off the sea surface. Was there loss? Was there poor reflection? Was there good reflection? Then I read two articles by Chinese scholars about sea surface reflections of RF waves. And I commend these articles to you if you're interested in this. The Lee article is entitled Reflections of the Multi-Hop HF Radio on the Rough Ocean Surface. And that the citation is there. And then there's another one that supports that also. And the Lee paper contended that for a smooth ocean surface, RF waves refracted down from the ionosphere were reflected as specular waves off the ocean surface. That's just like optics. Angle of incidence equals angle of reflection with virtually no loss. So that began to become interesting to me about the smoothness of the ocean surface at the reflection points. I sent that data to those papers to Carl, K9LA, and he reviewed them. And then he did some calculations based off the figures in the Lee paper. And he said, quote, the Lee paper's figure 3 gives the reflection coefficient for the HamSCI versus frequency. At 7 megahertz, it's about 0.975, 1 being perfect. Thus, 20 log 0.975 equals minus 0.2 decibel loss at the surface. That's for the smooth sea. For the rough sea, the reflection coefficient at 7 megahertz is about 0.5. Thus, the 20 log 0.5 is a negative 6.0 decibel loss, which shows 5.8 decibel more loss per hop per reflection due to a rough sea compared to a smooth sea. So that's kind of interesting now. This smooth sea is apparently making a big difference. But then I'm thinking, how can the biggest ocean in the world have smooth seas? So I discussed the findings with a sea captain ham pal of mine, and we both concluded that a physical cause might be the summer North Pacific highs. And any sailor, we're both sailors and merchant mariners, and there's a Transpac race every summer from Los Angeles to Hawaii, and the trick to that race and the bane of racing sailors is the easternmost North Pacific high. These are sometimes oval blobs about 800 miles in diameter of high pressure that must be skirted in order to avoid sailing through their middles, where the water is often dead calm, mirror flat with zero wind. And frankly, after I thought about it, it's probably why Magellan called the Pacific Ocean Pacific, because he probably ended up sailing through a couple of these things.
I'm so sorry, Larry, but we are running out of time.
Anyway, I did some more research, and then I found this piece from one racing sailor. Within the high pressure area, winds typically are light or non-existent. In June or July, for example, winds outside the high might range from 10 to 25 knots, whereas winds inside would range from 0 to 10 knots, the lightest wind strengths being positioned near the center. Indeed, when our sailboat has been positioned near the center of the high, we've seen mirror smooth, seemingly painted ocean. Sometimes the only thing left to do is swim in 18,000 feet of rippleless crystalline water. And there's a citation from the Ocean Navigator magazine. So
Larry, we're at time, but you might wrap it.
Okay, anyway, if you can go to the next slide. Keep going. Anyway, that shows the Pacific highs on that day. If you can go further, that shows then I had to check back one, please. That shows the wave heights, the National Weather Service wave heights, which we checked and are actually at least 30 to 40% higher than ground truth wave heights. So we're basically looking at 1 meter or 3/4 to 1 meter wave heights on the day of that propagation event. Anyway, if you want to look at this further, I've checked further, and there's tabular data where I checked over 12 years of July highs and wave heights and the number of JA spots in the RBN to confirm. And it convinced me anyway that these long-lasting Pacific high-pressure centers and relatively smooth water under them are what enhance the Pacific 7 megahertz propagation.